Well, welcome for the final 2D Stacy seminar of the semester. And it's my great pleasure to introduce Eilam Yalon. He is a professor of electrical engineering at Technion, Israel Institute of Technology. He earned his bachelor's degree in materials engineering and physics in 2009 and his PhD in electrical engineering in 2015, both from the Technion. After that, he went to Stanford, where he was a postdoc for 3 years with Professor Eric Hoff. And then he returned to the Technion as an assistant professor, and now he's a professor there. He has received several fellowships and awards, including the Intel Rising Star Award in 2022, the IBM Global University Programs Academic Award in 2021, and the Elin Roman Silbright Fellowship in 2015. So we're looking forward to hearing your presentation, and I thank you for coming.
Okay, thank you for the kind question. Thank you for having me for this seminar. So my group's work on various aspects of device physics, mostly focused on energy efficiency. We're looking at transistors, shooting materials, doing thermal measurements, and we're also working on memory devices. So most of this presentation is going to be about the memory aspect, but I'm happy to discuss some of the other topics offline. And I kept the title is fairly broad about memory, so from electrons to atoms and ions, rethinking memory switching mechanisms. They'll explain what I mean with this title in the introduction. So starting from looking at the big picture in terms of energy consumption, and it's kind of stating the obvious that with the rise of AI and the consumption from data centers, our energy consumption increases at faster rates. And to make this more sustainable, we need to improve the energy efficiency of our electronics in general. And if we're looking at device physics, we should be interested in the energy efficiency of our devices. And it always needs to be there. And so this, of course, has various levels. We look at it going from system level, device level. We've had for quite a long time what we call memory wall, which essentially means that the performance of our memory technology doesn't scale as fast as the computing elements. And more recently, in the context of AI and large language models, the memory doesn't scale as fast as the transformer size. So we need to focus efforts on our memory devices. And this, of course, goes back. It's not only about performance, it goes back to the energy consumption, because when we do this kind of operations, these are two examples for abundant data applications, and we look at the energy consumption. Most of the energy is consumed by the memory element or by data transfer between the memory and the computation element. So overall, motivating us to look at memory technologies. And if we look at today's memory technology landscape, which hasn't changed, the structure hasn't changed much in the last few decades. And I think it's fairly known, but just as a reminder, so it has this pyramid shape where at the base we have our storage devices like hard disk drive and solid state drive or NAND flash, which have high capacity or high density at relatively low cost, but they're very slow, not high performance. And these are storage elements, so they're non-volatile. At tip, we have our highest performing devices. Essentially, are silicon CMOS transistors just arranged in flip slots or SRAM. We saw us at the talk earlier today, saw that this SRAM again doesn't scale as much. So these have limited density or high cost per density, and they are volatile. They constantly consume power. And in between, we have the main memory, which is essentially DRAM, dynamic RAM, which I will explain briefly in the next slide. So the density is much higher than SRAM, but performance is better than storage elements. So it's somewhere in between, and it's a volatile memory. It requires constant refresh. And some of the evolution in the last 2 years was mostly concerned with packaging, not significant changes at the device level. So this is what we have today. And again, just to put everyone on the same page about what is DRAM and flash, I will explain briefly. So DRAM this is the original patent from IBM from 1968 by Bob Denard. Now it's the most influential patents by IBM. It's essentially capacitor that stores charge, that's the memory element, and access transistor to select the device and charge and discharge the capacitor. And because the transistor has finite leakage current in the off state, the capacitor gets discharged and we have to refresh. And that's why it's a volatile memory. And this cartoon shows roughly what DRAM looks like today. We have the silicon resistor, and we have this high aspect ratio cylindrical shape capacitors, MIM metal insulator metal capacitors, because we want to get high capacitance per area. So very briefly, that's DRAM, and looking at flash or non-flash, that's basically a transistor with either a charge trapping layer or a sloping gate that stores charge. This is non-volatile element because we need to apply relatively high voltage to charge and discharge these electrons from a charge trapping or layer from the floating gate. These are NMOS transistors, and we can connect them in series, this chain of transistor in a NAND architecture, which is compact and dense. And today we have 3D NAND. So these yellow pillars are polysilicon transistor channel. The green lines are the control gate electrodes. And then by stacking multiple layers, we can further increase scaling, get higher density. So that was very briefly the technology we have today. And what's common to both flash and DRAM is that they are charge-based memories. And as such, they have some fundamental limitations that we can understand just by looking at a very simple energy Venn diagram. So consider the electrons or the charges that we have in our memory surrounded by some energy barriers. In the flash transistor, these are, of course, the oxides surrounding the charge trapping layer of floating gate. In the DRAM, on one side we have the capacitor, on the other side we have the barrier to go to the transistor channel. And so the amount of electrons that we can trap, but it is determined by the device structure, so its capacitance and the voltage that we apply. And these charges can escape or leak by thermionic emission over the barrier, emitting through the barrier. And we know these other two physical processes, so we can make some predictions and some basic analysis of the limitations. I'm not going to go into precise numbers, but just roughly speaking, for a non-volatile element like NAND flash, that sets very critical limitations on the thickness of the oxide and the materials that we can use, because we want to have fairly large barriers to get long storage time, long retention time. So that these are some basic limitations for scaling. And we need to use relatively large voltages for the programming. If you want to do the programming at short time scale, we need to overcome those barriers significantly. So we need to apply relatively high voltages. This is for the flash. For the DRAM, we need, as we already saw, we need to have very high capacitance per cell, or some minimal amount of capacitance per cell, because we want to be able to sense those charges and move electrons. And again, there is leakage currents which limit thickness. So overall, DRAM and flash is what we have in our devices, from smartphones all the way to data centers, and they sell as well, but they have some very critical limitations of scaling. And because of what I mentioned earlier, with the increasing demand and limitations for memory, it makes sense to look at alternative technologies which are not charge-based memories. And there are various emerging technologies, so-called emerging, which some of them have been emerging for decades. Some of them were commercialized, discontinued, and so on. And each of them has their own different physical mechanism or principle of operation. There are phase transitions, resistive, magnetic, ferroelectric. Not going to go into details of each one of them, but just generally speaking, because they're not charge-based, they can overcome some of these scaling limitations, but they have their own challenges that we need to solve. So what I'd like to focus on next is about ferroelectric memories, and I'll explain why. And at some point later in the talk, I'll also discuss electrochemical one, or ECRAM. And all of these memories have long list of requirements. Like we want to be able to integrate them with CMOS or silicon processes. We want to have random access to access them individually, high capacity, high endurance, low power, low energy, and so on. So we know basically what we want from memory devices, and can be application dependent. And so for each of these different technologies, we need to look at some various aspects. So that's kind of the general takeaway. So now I'm going to talk a little bit about ferroelectric memories. So I'll start with a simple baseline. Again, this might be well known to some of you, but just to put everyone on the same page, very brief phenomenological description of ferroelectricity. We're talking about materials that have built-in dipoles or some spontaneous electric polarization that can be switched with electrical field. And these materials are composed of, this ferroelectricity or polarization is composed of domains. So if we look at the polarization versus applied electric field or voltage, we can see that by applying external field, we can switch those dipoles or domains. So the transition here is not abrupt because we have the domain structure. And then when we remove the bias, we have some remnant polarization, and that's what makes them ideal for non-volatile memories. Okay, so we have reversible switching between those polarization states. That's very briefly. And the origin of the phenomena is some non-sample symmetric structure of the material. Now, ferroelectric materials and memories have been known for a while, for over a decade, but still we don't use them. So that I just showed earlier that we're using flash and DRAM, and we don't use ferroelectric memories high volume in our devices. And one of the main reasons is that the ferroelectric materials that were known to us up to not too long ago, some perovskites are not CMOS-compatible, and they couldn't be scaled below roughly 100 nanometers. So they don't show ferroelectricity generally below about 100 nanometers. So they have very limited integration and limited staining. And that changed in 2011 when it was reported that hafnium oxide, the high-K dielectric that we already use in our CMOS processes, can show some metastable ferroelectric phase. There are a lot of details about how to prepare the material in that phase and insert some doping and write metal electrodes, experiment and so on. But without going into the details, it's based on hafnium oxide, and it shows, and importantly, it shows ferroelectricity down to a few nanometer sequence. So, like I said, ferroelectric materials always shown good memory properties like high endurance, low powers, and high speed. But now with hafnium oxide-based ferroelectrics, we have CMOS-compatible and scalable ferroelectric materials. So we then that first put ferroelectric memories back at the front of non-volatile memory research. And within that research, what I would like to show next is some studies of the switching kinetics relation between voltage and speed of these ferroelectric devices and materials. And there are various ways to use the ferroelectric material in the device. The two that I will show are ferroelectric DRAM, which is essentially a ferroelectric capacitor connected to a transistor. So it's similar to the DRAM structure, but with a ferroelectric capacitor instead of just a dielectric capacitor. So this is a non-volatile memory element. And the other one is the ferroelectric transistor, which I will discuss later. And to characterize ferroelectric capacitors, so this is an example of metal ferroelectric metal. It's dinitride, hafnium zirconium oxide, 8 nanometer thick dinitride. The way, one of the main ways to characterize their polarization is the positive up, negative down, or AND technique. Well, we first initialize the film to a non-state, for example, with a large negative pulse, and then we apply two consecutive triangular pulses, positive and up. So within the first pulse, the polarization will switch, and it will measure polarization current. So we are essentially applying voltage and measuring current. So the first pulse, within the first pulse, we'll measure polarization current because to compensate for the polarization charge. And then it's just discharge of the capacitor. And then the second pulse will only show charging and discharging of the capacitor. So then if we subtract the current from of the second pulse from the first pulse, we get the net polarization current. If we integrate this current, we get polarization versus voltage. This is the polarization voltage curve. And the voltage that it crosses zero polarization is called the coercive voltage or coercive field, if you know the field. And that's essentially the way we characterize those capacitors. And so within this, we're interested in switching kinetics or time. So there is a characteristic time schedule or frequency to this measurement. That's what one of the things we're interested in. By the way, feel free to stop and ask questions at any point. If it's too detailed or too fast.
Let's go.
Okay. So this slide shows this polarization voltage measurements. These are measurements, these are simulations with varying frequency and relatively limited range, in this case between 5 hertz and 500 kilohertz. this shows the current, the polarization current and the polarization charge versus voltage. And you see that there is some time or frequency dependence, which we can capture with the nucleation switching model. That's the model that is generally used for these materials. It basically means that there is switching time that depends exponentially on voltage and some activation energy and temperature. So this is a fairly general model, not specific to ferroelectrics, but for processes which are limited by nucleation. And there are some details of the models here. So basically, these materials, I won't spend too much time going into details, but because of this domain structure, so you have nucleation and growth of the domains, and nucleation of these domains is the rate limiting step. And that's why we get this dependence of time on voltage. But one of the issues with these type of measurements we were looking when we want to study kinetics is that the time in voltage, so the switching time depends directly on the voltage, and in this type of measurement, we vary voltage and time together. So a better measurement to look at switching kinetics would be to decouple the voltage to the time. So what we're doing next is some modification to that measurement, where we again first initialize the film to a non-state, for example, with negative voltage. Then we apply a rectangular pulse, where we can decouple pulse width and the voltage amplitude. It's challenging to get polarization current within that measurement, but what we can do is we can, following this pulse, we apply the two triangular consecutive pulses in the opposite direction, and that will give us the amount of polarization that switched in this pulse. So we call this a line readout because we read the current here, but we get information about the amount of polarization that switched within this pulse. And now we can vary the pulse width and voltage amplitude separately, and that gives us the full switching kinetics. So what you see here is polarization versus time. Each marker here is a measurement, like I showed in the previous slide, with pulse width, that's the x-axis, and the varying voltage amplitude. So in this case, varying between half volts and 2 volts. So now we can get the full switching kinetics across a few orders of magnitude in time, and we can use that to our models to feed and extract some information. What I'm showing here is our measurements for a large area device, 100 micron by 100 micron capacitor. And one of the things that we're interested in is looking at the high-speed operation. So in this case, we're limited by the RC of this ferroelectric capacitor. So whatever we have below about 100 nanosecond is not the intrinsic polarization switching speed. It's more parasitic. So to throw this short time scale, we fabricated smaller area and RF-compatible structures.
Here, handles.
So we're using high-sensitivity substrates and transmission lines for the pellets bouncing the ground, and smaller area capacitors. And now we're using another slightly modified measurement scheme. We again initialize the film to a known state. Then we apply 2 nanosecond scale pulses, triangular pulses, and we read the current within this pulse. So we get the polarization, the dynamic measurement of the polarization in the nanosecond regime. And then we also add this readout in the opposite direction to get the amount of polarization that's switched here. And this happens at the longer time scale where we know our measurement is accurate. So let's see what we get. So here we see so in black is the voltage across the capacitor. This is not the voltage that we applied from the pulse generator. It's the actual voltage on the pad, which we measure with an active probe because there is some reflections and some of the power dissipated across serial resistance and so on. So that is the black curve is the voltage across the capacitor. The dotted line is the current from the first pulse that includes the polarization and charging and discharging. So that's the positive. The dashed line is the current from the second pulse, the up pulse, which only includes the charging and discharging capacitor. And the solid blue line is the difference between the two, which is the net polarization. So we can see that this is for 4 micron or by 4 micron devices. These are still fabricated by photolithography. So that limits their dimensions. And we can see that for these dimensions, we get sub-nanosecond switching. So in this case, the half width, the width half maximum is about 650 picosecond. And if we integrate this curve, we get the polarization from the dynamic measurement, which you can compare to the polarization from the blind measurement. And there is about a 10% difference at this short time scale. Once we go to, with the same technique, if we go to 10 seconds and longer, they match. So we know that at the short time scale, we lose some of the signal because of lower signal to noise at the short time scale. But overall, we get a pretty good picture of the dynamics of the switching, and we get the net polarization charge from the blind readout. So with that, we can now vary the voltage amplitude and pulse width down to short time scale. And this is a heat map, and this is the polarization versus pulse width for both positive and negative pulses. The markers are measurements. This is from 400 picosecond to 10 nanoseconds, only covering the short time scale range. And the lines are models using this nucleation switching with some Lorentzian distribution of the degrees. So, but essentially, it has this exponential dependence of the time on the switching voltage. From the nucleation limit. And for the 4 micron sample, we extract, so we can extract the minimum switching time with at very high voltages. That would be about 75 picosecond for these 4 micron capacitors. So if we scale capacitors below micron, we expect switching the minimal switching time on the order of 10 or maybe below 20 picosecond. And of course, the challenge with small capacitors would be to be able to probe the current, something that we are working on next. So that summarizes the sub-nanosecond switching of ferroelectric capacitors, find with stiffers and the drums. Okay, so next we're doing a similar study for ferroelectric transistors. Ferroelectric transistors are basically field effect transistor. We integrate a ferroelectric material at the gate electric, and the orientation of the dipoles shifts the threshold voltage. For this study, we're using devices that were fabricated by global foundries in 28 nanometer bulk FET process. So they have an interfacial layer of silicon oxide, about 0.8 nanometers, and then 10 nanometers of silicon doped hafnium oxide, which is the ferroelectric layer. And so the results that I will show, we're using transistors with width and length of 240 nanometers. So here we can test much smaller area devices because we don't need to measure the polarization current. We can just probe the shift in the threshold voltage. So we can do that for smaller transistors. This is the kind of quasi-static transfer curve, IDVGS, showing the two threshold voltages, high and low threshold voltages associated with the different polarization states of the ferroelectric material. And the hysteresis is in the direction of the ferroelectric polarization, not charge trapping on the channel, which shows the opposite direction. Of course, that by itself is not sufficient to show ferroelectricity. There are other details which are not shown here. But that's a general transfer curve for these ferroelectric transistors, showing a memory window of about 1/8. And without going into the details, but we did a similar measurement where we applied pulses with varying voltage amplitude and pulse width, and we measure the change in the threshold voltage. And what is shown here is a heat map of the memory window. Okay, so 100% memory window is the 1 volt that we saw earlier. And this is for both positive and negative pulses, so photon and arrays. And it goes down to 300 picosecond pulses. And you can see that we can switch those devices at 300 picosecond if you apply sufficiently large voltages, about 5 or 6 volts in this case. And you can see that this switching kinetics across more than 10 orders of magnitudes in time. And we can assign a switching voltage of the 50% memory window. We then plot the switching time versus voltage. Again, use this simplified nucleation switching model to fit the data and extract some information. So in this case, with a smaller area, the extracted minimum switching time is a few picoseconds. And switching kinetics is fairly simple. Okay, so that was about the switching kinetics of electric capacitors and transistors. And what I'd like to discuss next is about ECRAM, electrochemical RAM, and we're using ECRAM with a 2D channel. So maybe there's a lot of activity compensatable 2D and also working with 2D. So that's the part of my presentation where I'm going to show some of our work with 2D materials. So the motivation to look at this electrochemical transistor, which I will explain next, is looking at synaptic devices for neuromorphic applications. And unlike the conventional memory elements, we have the distinct levels. And 2 levels are sufficient, like 2 states, which we have in our ferroelectric devices. For synaptic devices, we would like to have kind of analog behavior with a large number of states and good tunability and precision of those conducting states, with good linearity in terms of the change in conductance versus the number of pulses, and good symmetry between increasing and decreasing the conductance or potentiation and dispersion, and so on and so forth. So for the purpose of these type of devices, we're looking for something that shows a very a gradual and linear change in the conductance. So one of the leading candidates for this type of application is electrochemical RAM, or ECRAM, which is essentially, it's a 3-terminal structure like a transistor. So we have two contacts or soldering contacts to a channel, and instead of the electric gate, we have an electrolyte in a reservoir. And the concept is that we have a reservoir of mobile ions, for example, lithium ions, and an electrolyte or some medium where these ions are mobile. And then with pulses from the gate, we can electrochemically drive ions into the channel and out of the channel. And ideally, these ions are serviced jointly the channel, so they modulate the conductance. So if we can tune their concentration of ions going into the channel and out of the channel, and if these ions are dopants, they change the conductance because they change the carrier concentration, then the change in the conductance is proportional to the ionic gate current, which we can tune with applied voltage or even current, multiplied by the programming time. So that's the amount of charge or concentration of charge that go into the channel. And so that's essentially linear to the number of pulses. So ideally, we can get very fine tunability of the conductance in the channel. And that's why we're interested with electrochemical ECRAM devices. Another advantage over some of the two-terminal structures like PCM and the FeRAM is that programming or training path is separated from the readout or inference path, so which make them generally more energy efficient. So there were a few nice examples of ECRAM in the literature. This is my first papers for this is from IBM. There's one from India Labs, which I'm not showing here. And there was a paper from MIT published in Science using protons as the mobile species. So these are all pretty nice demonstrations, each with its own problems. These were used lithium phosphate, which is difficult to integrate in the processes. This is using polymer gel, and the MIT work again used protons, which is very unstable. But these were nice demonstrations for the performance of ECRAM devices. But still, there is a clear trade-off between speed and voltage and energy efficiency, and we're still looking for a CMOS-compatible, fast and efficient ECRAM device. So our proposal is to use 2D material as the channel transistor for several reasons. And so one of the reasons is that it's atomically thin. Okay, so there is no redistribution of these mobile ions within the thickness of the channel. And the other is that it's a crystalline material. So that has certain advantages over the previously used like amorphous oxides like tungsten oxide, which is generally most works use tungsten oxide in a heavily degenerate material. So the 2D material is atomically thin, it's crystalline, has some advantages. So we went ahead and fabricated. There's some details here, and we tried various configurations, but what worked for us eventually was for the so-called electrolyte, we just used thin aluminum oxide film. So it's not really an electrolyte by definition, it's just a very thin film. And then we used lithium as the mobile ion, and we introduced this reservoir or source of lithium. In this case, it's lithium cobalt oxide, which is for the conducting in this part of the gate stack. So this is what worked for us. For the 2D channel, we're using here a bilayer MOS2, and it's on top for processing issues. We didn't want to sputter on top of the 2D layer. So this is our device structure. There is a whole lot of source drain to gate overlap, and 3x1 weaken. Yeah. Okay, so these are some of the characteristics of our devices. And what's interesting is, compared to the previous ECRAM devices, is that we get both field effect or electrostatic gating, as well as the ionic gating, in addition to the ionic gating. So the ECRAM devices that I showed earlier with tungsten oxide, they were kind of programmable resistors. They didn't have a field effect from the gate, no electrostatic control. In this case, you can see that there is some hysteresis. So if we sweep a number of times, you can see that overall changing conductance, so the memory effect from the ionic gating, but in addition, we have electrostatic gating, which is shown with log and linear scale. And that is useful because it can act as a self-selecting element, and we can reduce the leakage current when the device is in the off state, because the leakage current is much lower with the electrostatic gating. So this is a demonstration of the conductance versus number of pulses, or potentiation and depression pulses. This is a signal cycle. And we can extract the nonlinearity coefficient of 0.5 and 0.3. We want below 1. So these are pretty decent linearity numbers. And the asymmetry is also pretty good. So 0.1 and minus 10.3 for the positive and for the potentiation and the depression pulses. These are something else merits that you can find. And so one thing to note, because it acts as a transistor, during the readouts, we apply gate voltage. So that's with advantage and a disadvantage. The advantage is that the off-state leakage is lower, but the disadvantage is that we need to apply gate voltage during the readout. And this is a demonstration of multiple cycles, and we have we went up to 1 million cycles. We had some issue with the measurement here, but I see 1 million cycles, pretty stable measurement. The device did not fail; it was just limited by test time. So I think it could be fairly stable. And just showing the retention up to 300 seconds. Again, kind of limited by test time because it's large number of pulses with long delays. So it's a decent vigilance and retention for these kind of devices. The lead power is fairly low because the conductance is just a few hundred picosecond because of this transistor gating effect. So that's useful for these kind of devices. So overall, that's a part of the to the ECRAM, and yes, do I have still time for the last?
Yes.
Yeah. Okay. So one last thing that I'd like to share is going back to the ferroelectric memories, but in a different direction. So these ferroelectric memories, as I mentioned, they weren't so. Their hafnium oxide was introduced in 2011, and all the memory companies have projects working on it. And it's become pretty mature. This is an example of work that Micron presented in IDM 2023. Well, they already show 32 gig array. They call it non-volatile DRAM. It's actually ferroelectric RAM. We saw it's the same structure, and they have multiple layers. The transistor is this polysilicon vertical channel because the transistor requirements are relaxed compared to DRAM. So it's pretty advanced. You can see the read-write latency and endurance and so on. But one of the main limitations remains that the readout without the polarization state is destructive. As we saw earlier, need to change the polarization, switch the polarization to measure the polarization current to read the state of the transistor. And that means that every time we read, we have to write. So we need to apply higher voltages, which are programming voltages, and it takes longer time and energy because of this write-back process, and the endurance is limited. So even though the write endurance is fairly high compared to some of the other technologies, it's about 10 to the 11, 10 to the 12, it's still not infinite. And because of this destructive readout, the limited write endurance also limits the read endurance. So this is one of the key limitations still of this technology, this destructive readout. And so people are working to find creative ways for non-destructive readout. And this is work that was done in Ionically, that are using the capacitance of the ferroelectric capacitor. So what is shown here is butterfly curve. It's shown as a dielectric constant versus electric field, but that's actually what you would measure in a capacitance voltage curve. And this difference in the capacitance is due to the different polarization state. And what happens is that zero bias, there is no difference in the capacitance, but the work that Ionically did here, they designed an asymmetric capacitor with a built-in field. So we just use different electrodes. Then with a built-in field, even at zero bias, there is a difference in the capacitance, and they read this difference in the capacitance to get a non-destructive readout. So that was a creative way, but it's fairly limited because the time to accumulate enough charge for this measurement was fairly long. It's about a millisecond. The memory window itself is very limited, very narrow. And because of the asymmetric structure, retention is also limited because there is built-in field that always distracts the state to no state. So building on a similar concept, what we proposed was, so this is, again, goes back to this butterfly curve of the capacitance versus voltage of a ferroelectric capacitor, which has different behavior of the capacitance in the different polarization states. It's programming in ways. So you would see that zero bias, this is an ideally symmetric capacitor, and zero bias, there's no difference in the capacitance, but the derivative or the change capacitance voltage has an opposite sign. Okay, and so and we can prove that different sign if we just look at the transient current when you apply a small transient voltage. So we apply a small voltage below the coercive voltage so that we don't switch the capacitor. And then for a very simple analysis of the transient current, we can see that we have the CTVDT term, the usual displacement current term. In addition, because it's a ferroelectric capacitor and the capacitance is not constant, we have an additional term of the change in the capacitance with time, which we can break the change of the capacitance with voltage and the change of voltage with time. So that means when we look at the transient, we have the capacitance term, but in addition, we have this term of change of capacitance with voltage. And that means that we can apply a small transient, even very close to zero bias, where there is no difference in the capacitance or a very narrow difference in the capacitance. And we need to apply very short pulses to get this signal, so delta t has to be short. But if we get that, then we'll see a difference that in the relay state, we'll have higher current because the CVP is positive, and the program state will have lower current because it's negative. And we're actually able to capture this phenomena. So this is, the dashed line is the voltage waveform 0.6 volts. It's about a nanosecond time scale. And you can see that when you apply this and measure, and the blue and red are the measured current in the program in the United States. You can see that it's fairly small, but you can see a difference. And then the fingerprint of this phenomena versus a change in polarization is that you see it not only when you went up the voltage, but also when you went down the voltage. You see this difference. And if you go to the opposite polarity, you can see that they switch, right? Because the derivative is negative for the programming state. So if you apply negative pulse, we will see higher the current here. So that's clear fingerprint of this line. So with that, we can we were able to. So in this case, we applied some short pulses to read out, and we got to 10 to the 13. This was limited by test time. The device did not. We did not distract the state. It preserved the state up to 10 to the 13. And this is just reading out the current, which is which doesn't show a very good memory. It shows a memory window, but not a very good one. But we can also read out the charge. And not only the charge, what we're doing is we apply two consecutive pulses, positive and negative, and integrate them. Because here there is a difference. We get this difference in the derivative directly from the difference between those two charges. So if it's in the program state, we'll get negative charge when we subtract one from the other, and in the erase, we'll get positive. And this is what you see here. So in terms of charge, we get a much clearer separation between the states, and it's self-reference, unlike the current. So for the current, we needed some reference, but for the charge, there is no reference needed. You directly get a positive charge in the erase state, negative charge in the program state, and it's non-destructive after the 10 to the 13 cycles. So we think that can be pretty useful. It's just benchmarking those non-destructive readout techniques. What we still need to do is scale down the cell area with the same 4 micron structures that we had with the photolithography. And the memory window is not as large as you would get in the destructive readout, but you can accumulate the signal over a few cycles and get. So there is a trade-off between the time and the memory window, but it's not destructive, so it has, in principle, infinite endurance, and it's faster and lower energy than the destructive readout. So it's not an issue to accumulate a few signals. Yeah, that's what I wanted to share. So I'll skip just one slide to thank my groups of the students doing the work, funding, and its collaborators. I'll briefly promote DRC, so please come and attend DRC in Michigan this year. And I can go back to this summary slide. I will just generally say, so I think it's important to work on energy efficiency of electronics, more specifically about memory. I discussed ferroelectrics and some aspects of ECRAM, and I'll be happy to take big questions.
Okay, are there any questions?
So in 34 of the slides, when you actually talked about two-layer analysis to lithium-based ECRAM, so I can see that actually the gate electrodes will already keep gold. Is there any particular reason to use gold as like policy electrode here, source string gate, over?
No particular reason. I think there were some processing issues. I can't recall. We did try other electrodes for the gate, which I think was tungsten. Yeah, there was no good reason for you. We just tried like 1 or 2 metal electrodes, and gold worked better. But other than that, there was no good reason to use specifically gold.
And the alumina uses a thin transport medium. A certain concern is that alumina may actually procure ammonia, so it will be difficult to pollute the channel. I believe if the thickness is not properly optimized, is 10 nanometer or easier for?
Well, the doping effect from the alumina is kind of a background effect, because what we're working with is modulating the conductance. So you would have some background doping from that electrolyte, whether it's alumina or maybe whether it's a different oxide. And in terms of the thickness, we validate the thickness when we developed the process, and I think it was, so this is patterned alumina, not ALD. For thinner films, the leakage to the gate was too high. With thicker films, we didn't get much effect from the ionic gating, so that was roughly the optimum that worked.
Sure. So, and in the 25 number slide, when you pop the book up based FEFET device, so from that image, I can see that ionic is a key, but on top of ionic, there's not only the not it is like easy. What's the purpose of this state?
Yeah, that's just part of the Global Foundries process, whatever they're using for their stack. It doesn't have a specific role with the ionic. So what is important for the to get the ferroelectric is at least nitride that's in contact with the hafnium oxide. Other than that, it's just whatever they're using. Thank you.
We have one online question that's been waiting. This is Rudra from Dr. Narayan's group. I'm sorry, I have not got that right. And he wants to ask if there are any size limitations for the non-destructive readout scheme.
Yeah, so that's a good question. I think in principle, no. But what we would like to do is, so we have those photolithography devices which we measured. We're working on an EBL process, which was slowed down due to various reasons. So we still don't have nanoscale devices. Obviously, measuring the nanoscale devices off-chip and redo off-chip measurements is going to be challenging because the area is small. The polarization charge, the absolute polarization charge is lower. So we'll get less current. But fundamentally, I don't think there's a problem. What we're going to do is we're going to scale down the devices and see how far we can do with the off-chip measurements. But ultimately, if you want to be serious about it, we will have to do some on-chip circuitry measurements. But fundamentally, I don't think there should be other side.
Thank you. I know there's more questions. Is there anyone who hasn't asked yet a question?
So it's looking for our ECRAM. So generally, when we talk about the electrochemical gating, so it's generally the electrolyte that actually gets, or it's the interaction of your ions with the channel material, right? But if you have alumina as your buffer layer, there is no similar interaction of your ions from your lithium side towards your channel side. So isn't it just ionic gating and not electrochemical gating? So I am a little confused between the ionic gating and the electrochemical gating.
They're essentially the same thing. It's an electrochemical process that drives ions in. So when I say into the channel, it's not clear whether this is a byte or MOS2. We don't really know where the lithium ions are, whether they go between the layers or they're just close to, the top of the layer or close to that layer. But we know that they change the conductance. And of course, there's some activation energy associated with it. Otherwise, you wouldn't have any retention, right? Because they will diffuse back as soon as we remove the bias. So there are some complexities here, which we don't have the details here. But we have some simplified TCAD models to capture the behavior, but we don't really know, and it's very difficult, to do this type of characterization. But the encouraging part is that it works. That's first. It's not even trivial to show that that is indeed an ionic effect and not some charge trapping. It's not charge trapping from the channel, that's for sure, because of the direction, but it could be some effect of charge trapping from the gate. I don't think that's the case, but it could have been in principle. Or we're doing some temperature dependence and other slip rate dependence ranges to try to figure it out.
Okay. All right. One more, then I think we'll wrap up. So I'll take it quickly. On your slide 41, do you think that current would affect your CV curve because it would distort the peak of the CV curve from your approach?
Leakage current doesn't, it is very fast measurements. Leakage current doesn't play any role because it's so much below. These are really huge, so it doesn't play a role in this review. Because the displacement current goes as delta T, it's 1 over delta T. And if you look at the current, so this is, milliampere current, because the delta T is so small, the leakage current is so much lower. So that's not an issue for this type of measurement. The leakage current can become an issue for, generally speaking, when we have, much thinner films. But if it becomes an issue, in that case, then it's also an issue in any polarization measurement, right? Because if you just consider the pan, in the pan, subtraction of the pulses is supposed to get rid of leakage current, but leakage current has some dependence on the polarization, so it's always there. When we do the pan, very slow pace, very slow amp rate, we see the effect of leakage current because then the displacement part becomes comparable to the leakage current. So the leakage current will become a much heavier issue in any polarization measurement before it becomes an issue here, because this measurement is very fast.
All right. Thank you. Okay. Well, thank you very much for a very interesting